Okay, we have the statement, surface area S of a cube, and of course you want to read the entire statement in the document. I've abbreviated the statements here. 6 times the area A of one of its sides, and we want to express that as an equation. So we get rid of everything but the essential things, which means we completely lose the meaning of the statement. But this basically says then that S is 6 times A. Okay, well, here we've got it. S equals 6A. S is 6 times A. That's what this is saying in terms of the symbols. Now you have to know that this is a cube and that this is the surface area of a cube. And then you understand, well, a cube has 6 faces, and each of those faces has the same area. So you multiply that area by 6. Over here, the area A of a square with side x is x squared. Okay, pulling the symbols out, that just tells us that A equals x squared, very simply. Now that is the area of a square, and of course that one's pretty easy to understand. The side of the square is x, then the square has dimension x by x, and it gives you area x squared. Now actually these two formulas can be combined. Really you're combining these two meanings and combining the formulas in terms of those meanings. How do they combine? Well, a cube has 6 faces. Each face is a square. So the edges of the cube are equal to the sides of the squares that make up the faces. So that if x is the length of the edge of a cube, then it's also the length of a side of each square. So A equals x squared applies to every one of the 6 squares that make up the cube. And we can then substitute x squared for A, and we get S equals 6x squared. And there's a formula for the surface area of a cube with edges of length x. Okay, here, this got a little messed up, but it says the area A of a parallelogram is the product of its base B and altitude h. Now if you take out all the meanings, this is saying that A is equal to the product of B and H. So A equals B times H. I put a subscript there. It's a PAR. That P's not written real well, but hopefully you can read it. That means area of a parallelogram is base times altitude. We'll apply that. Well, and I did that to distinguish from the area of a triangle, and I talk about that as kind of an addendum here. Let's go on to this one, though. It says the volume V of a solid with uniform cross-sectional area A is the product of that area and the altitude h perpendicular to the cross-section. As an example, think of a uniform cylinder. It's got a uniform circular cylinder. It's got a circular base. If you cut it, okay, parallel to the base, at any point, you're going to get a circle that's the same size as the base, the circular base. So that's called the cross-sectional area. Any cross-section parallel to the base is going to give you the same area. And of course, then you've got an altitude. So this would apply to a cylinder. You just take the product of the area A of the cross-section, which is equal to the area of the base, and multiply that by the altitude. And the caveat, the altitude is measured perpendicular to the cross-sections, which means perpendicular to the base. So the formula is very simple. V is the product of the area, and the area is A, and H. Okay? Take out that much of the statement, and you get V equals A times H. We'll apply that in a later question. Okay, triangle. Just to generalize a little bit, or just to get one more result here and see where it comes from. Any triangle, we think of this thing down here as being a triangle. Of course, that's the way it's sketched. And I'm going to kind of erase what I through here just so I can draw it again. Kind of messes up the picture. But if we have a triangle with a base and an altitude, and remember altitude is always measured perpendicular to the base, well, we can take a copy of this triangle and flip it around this vertex, and we get a congruent triangle here. And up here now the base is going to have flipped up to here, and the altitude will be here. Okay, so this triangle is congruent to this one, whether I drew it that way or not. Well, that makes a parallelogram. Now, you've got to do geometric argument to see it, but it's not a complicated geometric argument. So we now have a parallelogram, and its area we know to be B times H. But of course we have two identical triangles that comprise that area, so the area of each triangle is 1/2 base times altitude. So that's where the area of a triangle comes from. Now the area of a parallelogram comes from something else. We can reconstruct any parallelogram into a rectangle having dimensions equal to the base and the altitude of the parallelogram. I haven't shown that here.